So tonight we're very excited to welcome Dr. Joan Bunbury from UW-La Crosse as our speaker. She's a professor of geography and environmental science at UW-La Crosse. She has a PhD, MSc, and BA in geography from University of Ottawa, Canada. Her research uses information stored in lake sediments to reconstruct past climate and past environmental conditions. Joan has conducted studies in the Southwest Yukon Territory and Hudson Bay lowland regions in northern Canada, and currently she has a project underway in southeast Wisconsin. She is a self-proclaimed climate geek. So everyone welcome Dr. Bunbury to tonight. Thank you.
Great. Okay, everyone can hear me? We're good? Great. So thank you, Beth, and thank you so much for inviting me here to give this talk tonight on climate change in the Driftless Area. So as Beth mentioned, my research uses information stored in lake sediments, and unfortunately there aren't any lakes in the Driftless Area, so I'm not going to be talking about the research that I do. I do have a bigger project that is taking place in southeast Wisconsin. A couple of I have some sediment cores collected from one lake in southeast Wisconsin that extend back 16,000 years, so that's really looking at climate change on long time scales. So what I'm going to be talking about here tonight is what's going on in the Driftless Area with respect to climate change on time scales that we can understand, right? So pretty much over the last century or so. So just kind of the last 100 years, the evidence that we have for climate change, and then also what some of the predictions might be for the future. I teach climate change in a bunch of my courses. I teach an Earth Environments course, which is an introduction to physical geography, if you will. A large part of that course is atmospheric, and so I do talk about climate change. We have a module on climate change. I also teach a polar environments course, and of course in the Arctic, we're seeing big changes in terms of what's happening with the climate. It's warming faster than anywhere else on Earth, and so I talk about climate change in that course. And then I also do teach a global climate change course, so I'll be teaching that. It's been a while since I've taught it, but I'll be teaching it again next semester, so I'm looking forward to that. So anyway, now on to climate change in the Driftless Area. So are you okay? Can you see okay over my shoulder there? Yeah, is that all right? Everybody okay? Good. All right, so first of all, because I'm not presenting any of my data from the research that I do, what I am using is I'm using data from a number of different sources that's available on the internet. It's amazing the plethora of information that you can get from the internet on climate change, and these are a number of those different sources that I'll be using. I'd also like to give a shout out to Jeff Boyne at the National Weather Service in La Crosse. Maybe some of you were at the open house that they had in September, and he had a slideshow playing that had some good information in it, and he actually shared that with me. And so I've used a little bit of some of the sources that he had, as well as a little bit of the information that he's presented I've also got in this presentation. And then the photographs I'm showing, the majority of them are from my personal collection, but there's also a few of them from the UWL photography, and so I just wanted to give a shout out to them as well, because our UWL photographer is really terrific. We've got some great photographs that are available on the web. So I just want to start with, I'm going to start big, right? We're going to start talking about climate change big, and then kind of get down into here in the Driftless Area. So the first place to start is what's happening with global climate. So this is a graph that is showing climate since, is this one 1880? Since 1880 is what we're seeing here. And we can see, it's intuitive, so we can see that those blue bars represent periods that were colder than a given average, and the red bars represent periods that were warmer than a given average. So that given average is this period, is this here. So what happens is you take an average for a year, and then you subtract from that this average over a long time scale. If your average for that year is colder than that long time scale, then therefore that's where you end up being on the negative side of this graph. If your average for the time period, or if you take an average, if we consider what's going on here since post 1880, post-1980, what we can see there is that our temperatures in a given year are actually warmer than this long-term average. So these are referred to as climate anomalies, right? So they're anomalous values that are represented based on some type of a baseline. And so in this case, the baseline is this period 1901 to 2000. So we can see 1880 to 1940 or so, conditions were cooler than that period from 1901 to 2000, for that century-long period. From the 1940s to the 1980s, a little bit of variability. Some years were warmer, some years were colder. And then post-1980, we're really seeing this warming that has occurred. Warmest year on record is, sorry, I'm getting used to my device here. Warmest year on record was last year, 2023, by far warmest year on record. 2024 has already been, I heard last week, 2024 is on track for being the warmest year on record. So it's going to beat out to 2023, so they're already on that track. Now, kind of move in a little bit more, we'll look at the national temperatures, so what's happening with national temperatures. We're seeing a similar pattern here. This is interpreted the same way. Anything below the line, colder than a given average. Anything above the line, warmer than a given average, based on either being red or blue. So and these ones happen to be in degrees Fahrenheit, but nonetheless, we're getting the same message here. So obviously, and this is since 1900, so a lot more variability compared to the global average. And that's because climate doesn't change the same way in everywhere, right? Climate is highly variable, and it depends on the locality that you're in as to what's happening in that region. But what is happening is post-1880, or 1980 rather, we're seeing this we're seeing this increasing trend in the same way that we're seeing with global temperatures. Maybe not every year, but for the majority we're seeing that. I just want to point out too is that we've got some other lines on here, and these data are this UAH, that's a data set, that's a remote sensing data set that has satellite data imagery that has been analyzed by the University of Alabama at Huntsville. And so that's these are their data that or the way that they've computed their analysis. There's also RSS, which is Remote Sensing Systems, I believe is the name of the company. And they've also done some analysis of remotely sensed data. And so we're seeing these overlaid on top of our climate graph. And the importance of this is that we're seeing three different climate graphs that are developed by three different ways that are showing the same message, right? They're showing the same thing. We're seeing the same trends in that data. So that's what the importance is of having those three different types of information. The information in the data from the bars is typically from, these are land-based temperature measurements. So these are temperature measurements taken by climate stations that have, a network of climate stations around the globe. We've got better data, we've got more climate stations in later years, but nonetheless, it's still all very reliable information. And 2012 was the warmest year on record in the United States. I'm not quite sure how 2024, I haven't heard anything about whether 2024 is expected to be the warmest year in the US, but we certainly know we've had some pretty warm conditions in various places. So certainly not the same warm year, right, compared to 2023. And again, just pointing out how that climate variability and the differences depending on the area that you're in. So now I'm just going to talk about the driftless area. So this is a map. It's actually a short paper. It's a short 2-page paper. Some of you may be familiar with it. It's a short 2-page paper that was put together in 2023 by Eric Carson at the Wisconsin Geologic and Natural History Survey, and he worked together. So he's in Madison, and so he worked together with some folks. He worked together with geologists from Illinois, a geologist from the Minnesota Geological Survey, and a geologist from the Iowa Geological Survey, to come together with what is this true representation of the driftless area. So it's called the driftless area because there is no glacial drift here. There have never been glaciers in the driftless area. So glacial drift is material that's left behind by glaciers, and the fact that we don't have any of that in the driftless area is why we call it the driftless area. So there's all kinds of other, there's all kinds of other delineations of what the driftless area is or the driftless region is, and that kind of expands into Minnesota and Iowa. But the true driftless area is found in Wisconsin, and then a little bit of it in Illinois. So this region has never been glaciated ever. So it's never been glaciated in past history. Over here in Minnesota and Iowa, and a little section of Illinois, they did have glaciers there at some point in the past. There have been multiple glaciations. There's been 20 plus glaciations over the last 2.6 million years. And these have influenced the landscape that we have here in this area, or here in northern North America. So these areas here have not ever been, they were glaciated at some point in the past, not during the last glaciation, but some, a period in time, like over 1 million years ago they were glaciated, but they haven't been glaciated since. So as a result, through erosional processes, this driftless style topography has developed. So that's what we've got here, is that driftless style topography, right? We've got these deeply incised streams, right? We've got steep, we've got the high bluffs along the Mississippi River, incised streams, and very sloped and well-sloped streams as well. So similar type of topography, but not truly driftless like we are here in southeast Wisconsin, or southwest Wisconsin, and that little northeastern Illinois, that little tip in northeastern Illinois. So now we want to, how does this compare with, what's the climate like, right? So I'm just kind of setting the stage for how we can look at what the climate's like in the driftless area. Because, we don't have climate that's, we don't nicely have a whole bunch of little weather stations all set up within our driftless area so that we can analyze the data and see what the climate's like. We have to find, those regions that fit best within our area. So here is a map just showing the Wisconsin climate divisions. And you can see, so this west central and southwest Wisconsin, these areas really are the ones that overlap best with our true delineation of the driftless area. So now where I'm going to get to is, so as we're moving forward here, I'm going to bounce around a little bit between kind of looking at national scale data. So we're going to look at temperature first, and then I'll look at precipitation. So we'll kind of look at national scale, and we'll bring that down into kind of more localized scale in the driftless area, and then I'll do the same thing for precipitation. So here is a map that is showing the rate of temperature change in degrees per century for the period 1901 to 2023. So what we can see here is that obviously redder, it's intuitive, redder would be warmer, blue would be colder. We're not seeing a whole lot of blue on there. There is some gray in the southeast that indicates there isn't a whole lot of temperature change. But if we consider what's going on in the driftless area based on our climatic division, we can see right up in here, we can see we've got about 0.5 to 1.5 degrees Fahrenheit change in temperature over this time period, or over that century-long time period. So that's what we're seeing in the driftless area. Now, if we start to look kind of from a different perspective, so if we look at what's happening with respect to, if we look at what's happening with respect to summers and the summer temperature, so again, this is the national scale that we're looking at here. So we've got the national scale, and this is the percent land area of the contiguous United States with unusually hot summer temperatures. So by unusually hot, I mean higher than normal. And I'll talk about normal in a few slides. So I'll discuss that a little bit more. So what this is showing, we've got a couple of different things here. We've got the lots of variability in those daily highs and the hot daily lows. And then those broader lines represent these are 9-year averages. So what they do is they help to smooth the data, so you can kind of see the trends more easily, dampen out that variability and look more at the trends. And so the message here is that we're seeing that we've got, right, since post-1990, we're seeing this increase in the number of days in these hot summer temperature days here in the United States. So the hottest point of the day occurs usually 3 o'clock in the afternoon-ish. That's kind of what we have here in this area. The coolest point of the day occurs right before sunrise, right? That evening, the whole nighttime of cooling, and then coolest temperatures typically right before sunrise, unless you get some big air mass change or something like that. But so what this is showing us is that we're seeing, right, it's not cooling down, it's hot during the day, and then it's not cooling down as much as at night. So that's what this is showing. And then here we're looking at the percent land area within the US with unusually cold winter temperatures. And we're seeing a decline in the number of really cold winter temperatures. So this is interpreted the same way. Oh, sorry, I keep hitting this thing, it keeps bouncing in on me. So this is being interpreted the same way, right? We've got lots of variability here, and then that gets smoothed out by these 9-year averages. And we can see post-1990, we're not seeing, we're seeing far fewer of those very cold days, or those cold daily highs. Right? Those colder temperatures we're not seeing in the same way anymore. And now if we look a little bit more localized, so here is, this is one of those maps that was, Jeff Boyne provided for me. But you can see here we're seeing this change. So we're seeing less extreme cold. Sorry, I think that jumped ahead of me. I feel like maybe this is on a play, but anyway, we'll see. So this is less extreme cold, so minus 20 degrees Fahrenheit. So we're not seeing as many days with minus 20 degrees Fahrenheit compared to what we used to be, right? If we compare the 1960s and 70s with the 80s and 90s and the 2010s, the 2000 and 2010s. So this light blue color, this is somewhere between 10 and 20 days of these minus 20 degrees Fahrenheit, whereas we had more of those in the previous decades. And then the same thing goes for the minus 30 degrees Fahrenheit. We're really not seeing these extremely cold temperatures in the same way that we were in the past. Okay, so now moving forward to look at precipitation. So this is the percent change in precipitation across the nation during the period 1901 to 2023. You can see it's intuitive. More change in precipitation is blue. Brown, beige, less precipitation that we're seeing. So obviously no big surprise, drier in the west, particularly the southwest, very wet in the central portion of the country and also in the northeast. Particularly here in the Driftless area, we're seeing, 10 to 20% increase in precipitation during this time period, or during from the 1901 to 2023 time period. This is not really a big surprise. Climate models back in the 1990s were forecasting that the middle portion of the country would start seeing wetter conditions, and that is what we're seeing. So those climate models were getting it right 30 years ago. So looking at the unusually high annual precipitation, so here we can see, again, this is the percent land area of contiguous US with greater than normal precipitation. So here we're back to this idea of normal, so just keeping that in mind, because I'll talk about that more in a couple of slides. But we can see that we've got, we're seeing there's a slight increase here. A little bit of a dip in 2021, but we are definitely seeing this increase in these, these areas that having higher than normal precipitation, the percent land area with higher than normal precipitation. And then what's also happening is we're getting an increase in these extreme one-day precipitation events. So a lot more precipitation falling in one-day events in the more recent history compared to the earlier part of the record. Right, we can all appreciate that, right? Having the extreme amounts of precipitation, and then what the consequences that has, particularly here in the Driftless area with these deeply incised streams, high slope, right? Those Coombe Valley was decimated back in 2018. I remember driving through there in 2017, right after a rainfall event, and then 2018 was even worse. So definitely problematic, these heavy one-day precipitation events. The system just simply can't handle that much water at one point in time. And then here, if we just look at the upper Midwest, so my previous slide was looking at the nation, and here we are looking at the upper Midwest, and we're seeing the same thing here. This is Minnesota, Wisconsin, Iowa, and Michigan, but still, nonetheless, post-1980, we are seeing this increase in the amount of precipitation in these one-day events. And then if we look at precipitation in Wisconsin, so 1895 to 2023, so you can see on the right-hand side of the graph, so there's that period, right? There's that, this is 2019. That's that wettest year on record in the United States and also in Wisconsin. So lots of precipitation, but then look at that, we dropped right off the next year, right? So it's, even though we get these several years of lots and lots of rainfall, it doesn't mean that we're not going to have, periods after that where we get a decline in the amount of precipitation. Okay, so now moving on, so now we're looking at climate normals. So this idea of what climate normals are, right? We hear it all the time, watching the news, warmer than normal, colder than normal, wetter than normal, drier than normal, whatever that may be. And so these normals, these are 30-year averages. We're currently dealing with a 30-year average from 1991 to 2010. These are computed computed every decade by the National Centers for Environmental Information. This is an organization that's under NOAA, right? The National Oceanic and Atmospheric Administration. That is the same administration that runs the National Weather Service. So what happened, every country is mandated by the World Meteorological Organization to compute climate normals every 10 years. So every decade they need to compute these data. Of course, there's some countries that are in a position where they've got bigger problems. They're not in a position to compute those climate normals. But here in the United States, Canada, European nations, they're all in a position to be able to report on these climate normals, to make that data available so that we can understand, what is normal, right? What can we define as normal? They are over a 10-year span because climate is so variable, right? The very nature of climate is that it changes. The temperatures today aren't going to be the same as tomorrow or yesterday, nor is this day next year going to be the same, nor is climate the same as it was last year, right? So it's changing all the time. So we need to be able to account for those changes within that variability. We need to account for that variability within climate, but also make it so we need to make it long enough to account for that variability in climate, but short enough to actually capture what is happening. So that's what those climate normals are for. So the previous climate normal period was 1981 to 2010. The next climate normal period will be 2001 to 2030. It takes the NCEI, it takes them about 6 months to produce the data. There's a lot of data that they need to compute to get these climate normals out for the nation as a whole, as well as the different regional areas. So I typically, usually they get posted sometime in mid-May or the end of May is when the climate normals come out following that 10-year period. So, and they, of course, provide the context for the current conditions, right? Is it warmer than normal? Is it colder than normal, etc.? And they're important also for understanding drought assessment, right? Is this really drier than it has been in the past, or is it wetter than it has been in the past? When can we expect freezing to occur? What's the usual time that we can expect freezing? It's important for energy usage, whether we need to cool our homes or heat our homes. It's important to be able to make these some estimations as to what what we can expect, right? We can look at these past data. Is it going to snow or not snow, or or is this a usual amount of snow, right? That this is important for city planners in terms of budgeting. How many days out of a year can they expect to have to be plowing and potentially treating the roads? And then of course travel, right? It's important for travel for us to know. Is this going to be worse than last year or better than last year, or what may that be? So these are important variables to understand the context for, and of course the importance of these climate normals. So here in Wisconsin, these are the climate normals. So this is the normals summarized for the entire state in one graph. So we've got precipitation, we've got mean annual temperature, mean annual temperature, mean maximum temperature, and mean minimum temperature. That's what is being shown on this graph. The lines represent temperature, because this is a continuous variable, right? We always have a temperature, whereas precipitation is represented by the bars, because either it rains or it doesn't, right? Either we have precipitation or we don't, or snows. So we can see here, and then we've got our temperature on the y-axis here, and we've got our monthly normal precipitation, or this is precipitation over here on this side. And then we've got our months of the year. So typically, obviously colder temperatures in the winter time, warming up in the summer, and then cooling off again. And we've got our wettest month is June. So here in Wisconsin, our wettest month for that period from 1991 or from 1991 to 2020, our wettest month has been June. Driest months tend to be during the winter time. That's pretty common for that. So now let's look a little bit closer. Let's look at our two regions, right? The west central and the southwestern portions of the state. And so we've got the west central on the top and the southwestern on the bottom. They show pretty much the same thing, right? June is the wettest month, is what we're seeing. There's really very little difference in the climate normals between the two. There are very subtle differences. You'd really have to look more closely at the data to see those differences. So, and no big surprise given that they're in pretty close proximity to each other. And from my experience living here, it seems that everything kind of above here, right? Either those storm tracks travel north, or they travel here, or they'll hit Eau Claire, but they won't hit further south. That's or they'll travel further south and they won't hit Eau Claire. But often Eau Claire tends to have more of a snowpack than we do, just a little bit further south, or potentially more precipitation. I mean, it can be it's hit and miss. It depends on those tracks. So here are, so what this is showing, we've got 3 bars on each of these, for each of the months here, and these are the normal periods. So we've got the blue bar, the light blue bar is 1971 to 2000 climate normals. So what we're doing, I'm comparing the climate normals here. So 1971 to 2000. 1981 to 2010 is kind of this darker purpley blue one, and then the green one is 1991 to 2020. So again, very subtle changes in what we're seeing with these climate normals, but we would expect that because these are averages over 30 years. So these are averages taken within this region, within each of these regions. It's a lot of data that is kind of averaged down, so we see these subtle changes. But what I saw in here is we're seeing this increase in mean annual temperature. So if we look at those green bars, right, September through December, we're seeing these increase in mean annual temperatures in both of these regions. So just that little bit of those little bit warmer temperatures that we're seeing over this last 10-year time slice. And I mean, that certainly holds true for the fall that we've been experiencing as well, right? It's been incredibly warm the past few months. Now the next one we'll look at is precipitation. So this is not quite as cut and dried as temperature. Temperature tends to be nice, a little bit smoother. Precipitation can always be a little iffier, because you need to have cloud, even because it's cloudy doesn't mean it's going to rain, right? And it can rain areas, further south or further north or just east, it can rain in one area and then, you can be driving along and all of a sudden it's not raining in the next area. So it can be a little iffier. So this wasn't so cut and dry, but certainly June continues to be the wettest month in both of these regions within the Driftless area. So what I summarized here, so we're seeing an increase in precipitation in April to June, pretty much across both of these. We're seeing that increase in precipitation. Also, September and October, we're seeing an increase in precipitation. And then December through February, we're seeing that increase in precipitation. The interesting thing about precipitation during the winter is that, is it going to fall as rain or snow? Well, it's only going to fall as snow as if the temperatures are cold enough for that to happen. So that's where we start to see changes in snowfall. And that's in our next graph. So looking at the normals for snowfall in both of these areas. And this, again, a little iffier, but we can see those declines in snowfall in January. And again, if we've got those warmer temperatures, then we're not going to get that snow. We're going to get rain instead, which you know, may or may not, whatever your preference is. Some people prefer not to have the snow; they don't want to shovel. But it can be extremely problematic in the springtime as to whether or not we're going to have that snowpack, because that snowpack, that snow melt in the springtime is so important for restoring soil moisture and groundwater. You know, extremely important, which we don't necessarily, we're not necessarily getting. And what I've noticed is that in the time, I mean, I've lived here for 12 years now, 12 and a half years, and it seems like we're getting high water in September and low water. I mean, I'm right on the Mississippi in La Crosse, so high water in September, low water in the spring. I mean, that's completely backwards. And that hasn't been every year, but that's certainly been, you know, I've observed that probably at least 3 or 4 years in the time that I've been here. So the summary, back to snowpack. So increase in snowfall during February, which I found kind of interesting. And April having more snowfall, certainly in the west central region. We're seeing more increase in snowfall in April. January tends to be highly variable, right? It's up and down. And March and November tend to be decreasing. So those shoulder seasons, right? If we're getting warmer temperatures in March, less snowfall. Having these warmer temperatures through the fall, we're not seeing any snowfall or less snowfall in November. Okay, so now I'm going to move forward and let's just look at a synopsis kind of in more recent history. So kind of what's happened over the past couple of years. So looking at this climate synopsis from 2023, there was lots of stuff going on. So here is the monthly temperature anomalies in Wisconsin for 2023. So what this is showing, you can see that all of these are above zero. So zero is so the baseline here is 1895 to 2023, or 2022 is what the baseline is here. So what this means is that all of these months, except July, were warmer than that baseline period of 1895. Actually, I think it was 1895 to 2000 is what that base period was. But still, pretty alarming that we're seeing those, every single period was warmer. Every single month was warmer than that base period, with the exception of July. January was the 5th warmest on record in Wisconsin. September was the 6th warmest on record in Wisconsin. And December was the very warmest on record in Wisconsin in 2023. And then July being colder than that average. And I think July was actually colder this year as well, too. I mean, marginally colder, right? Certainly not to the point where we have to pull out our duvets and wear winter coats or anything, but it was definitely, you know, certainly, it didn't feel like it was as hot. I think that's what I observed personally. And then if we look at precipitation anomalies for 2023, again, so here we can see, this was, when I looked this up, this data, or these graphs were from the state climatologist's office, which is at UW-Madison, and they called this precipitation ping pong, is what they referred to this graph as, right? Because we've got the very wettest January to April on record in 2023, 4th driest May to August, and then it was wet again in October, and dry, 8th driest in November, and then a little bit wet again in December. So this back and forth each month, seeing these increases and decreases in precipitation. And then the accumulated precipitation, so this is the, so what this is showing, so this is January 1st to December 31st on this graph, and what this is showing is that, you know, we've got a lot of beige on there, a little bit of green in the kind of northwest portion of the state, but we're seeing lots and lots of beige and red, so drier than normal. So these are, and this is relative to those 1991 to 2020 normals. So we're seeing very dry conditions. In both Vernon and Crawford counties, 12 inches below normal in terms of the amount of precipitation for the year last year. So that's pretty significant. I'm sure many of you either felt the effects of that or know people who felt the effects of that. And then looking at winter 2023-2024, so the meteorological winter runs from December, January, February is when the meteorological winter runs. And so here is, this is a graph showing Wisconsin average winter temperatures from 1895 all the way up to 2024. And we can see very warm winter in that 2023-2024 winter was very, very warm. So that was through December of last year into January, February of this year is what that's showing there. And then we can even see that those winter temperatures are just generally warmer. They're trending, here's the average there, so they're definitely trending above that average, and that's kind of since 1985 or so. So here is the accumulated snowfall. So this is, again, this is December 1st to the end of February, December 1st, 2023 to the end of February 2024. And this is the departure from 1991 to 2020, or departure, same thing as the anomaly, or, you know, that was the baseline being used here. And we can see that, you know, very little snowfall, right? We have hardly any snowfall, certainly La Crosse, yeah, we didn't have much snow last year at all. And the majority of the state really saw lower amounts of snowfall. So those warm temperatures were in response to an exceptionally strong El Nino. There is no clear, there's no clear pattern for what happens with temperatures here in kind of in the Midwest or in the central portion of the country relative to an El Nino event. El Ninos can be very strong, they can be weak, but they still exist either way. Typically when they're weaker, they have less of an influence. So, but there's no clear pattern with, you know, a strong El Nino is going to give us warmer temperatures, right? Like that isn't a given thing in the, you know, that's not a given in this region. But certainly, you know, this was something that was reported by the state climatologist's office, that it was these warm temperatures, particularly in through our winter last year, were El Nino combined with that long-term warming trend is what contributed to those warmer temperatures. El Nino is now gone. I think we're sitting in neutral conditions. We might have a La Nina coming, but it's hard to say. I think they're still keeping an eye on that. El Ninos and La Ninas tend to be strongest during the winter time. They usually develop kind of November, December, and then or October, November, December, and then they persist through January, February, March. The reason why is because you end up with those strong temperature gradients, right? In the northern hemisphere, we've got colder temperatures during the winter time, warmer temperatures in areas to the south of us. So therefore, once you get that strong temperature gradient, it allows for these large climatic phenomenons to set up and to have more of an impact on overall climate. Now looking at summer 2023-2024, wet. I mean, right, with very, very wet. Crazy. July 4th in La Crosse, it was all underwater. The whole Pettibone campground was underwater. People couldn't be there to watch the fireworks or anything like that. It was like crazy wet year. So this is June 1st to the end of August, so the meteorological summer. And we can see, you know, we're anywhere from, you know, 2, 4, 6, 8, 10 inches above normal. So that's pretty significant, the amount of precipitation. So we had a rainfall surplus, we had a lot of intense downpours, record Mississippi River water level at La Crosse, which I'm going to show you on the next slide, and then dam failures, right? I know there was a dam failure in Wapaka County in the middle of July. There was dam failures in Minnesota, that Rapidan Dam that was in mid-central Minnesota, or south-central Minnesota, that failed. That was, you know, pretty horrific seeing these major dam failures. And again, you know, not uncommon for people to understand also from this region, right, with the Coon Creek flooding. So here is the two longest and largest Mississippi River summer floods. So this is 1993, which was that was the last big flood, and then 2024. So 2024 had this odd flood. So first of all, I'll just show you this graph. So here's the 1993 line that kind of runs up here and along here. And oh, there it goes there. And then here's the 2024 line, because it's kind of overlain on the It's also overlain on the daily max and the daily average, which is why it changes colors a little bit. So here we can see, and there's that period in 2024 where, you know, the end of June all the way through middle of July or so, it was very, very high water. Here's a photograph that I took in Riverside Park back at the end of June, June 29th, I took that photograph in Riverside Park. So just some comments about this flooding. So both of these floods were the 5th longest for any flood of 12 feet or greater. So here we've got the action stage is 10 feet stage. So this is at La Crosse. These are the stages at La Crosse on the Mississippi River. This is the 12-foot stage, this is 13-foot stage, and that's the 16 or 15.5-foot stage up there, which is the major flood stage, which we didn't reach. But still, you know, 12 feet or greater, that was a pretty extended period of time where both of those water levels were 12 feet or greater. And then 2024 was above 14 feet for 12 days. So June 27th to July 8th, it was 14 feet or greater. And then 41 days, from June 9th to July 19th, 2024 was 10 feet or higher. So it was at that action stage. Like, that's an extremely long period of time for those water levels to be so high at that time of year. And then things change pretty quickly. September 3rd, we start to go, right, we see September 3rd, we're starting to see some areas with abnormally dry conditions. October 1st, a lot of areas with abnormally dry conditions, and even further moderate drought in the northern parts of the state. And then by the time we get to November 5th, I just pulled this off the internet the other day, we can see that we've got abnormally dry and moderate drought within the driftless area here, right? So we're seeing, you know, again, there's that seesaw or that ping pong kind of effect, right? Back in July, we had more water than we knew what to do with, and now we don't have any of it. So September was one of the warmest and driest on record for Wisconsin. I mean, it was lovely weather. We had banner weather. It was, you know, perfect, right? 75, 80 degrees, no rain. I mean, it was ideal weather. I live right near UWL in student territory, and they appreciated the warm weather too, because they were all outside partying, so. Okay, so now let's look at what 2024 is to date. So we can see, so here are these lines here, so this orange line, this is the normal. There's our 30-year average, so we can see how that's smooth. And so this is our 30-year normal high temperature, and that's our 30-year normal low temperature. So we can see beginning of the year, in mid-January, we had a little bit of a cold spell, but then we've been kind of warm. We were a little bit warm, February, March, and then July, or look through the summertime. The data is just hugging right along with that line. There's not a whole lot of variability, right? There's those kind of, I mean, the summer wasn't cooler, but it wasn't as hot, or it wasn't as different from normal as other times of the year. And then here we are now, and then consistently, this is pretty consistently above normal that we're seeing here, kind of post, you know, September onwards. Even August, we had some warm weather towards the end of August. And then our precipitation, we can see these bars here, so we can see, you know, we had lots of precipitation early part of the year, but there are those gaps. We haven't seen a whole lot of precipitation in those, you know, from August all through to the end of the year. These lines here, this staggered line, the black one, is showing the cumulative precipitation for the year, and the green line is showing the average precipitation for the year. So we're pretty much right on average, even though we've had kind of this inconsistent precipitation regime that has set up over the year. And then seasonal temperature outlook. I always show this to my students when this first comes out. So here's what we can expect for December, January, and February according to NOAA. So we're seeing, so what this is probabilities. That's how they present these maps now. What is the probability that it's going to be warmer or colder? And so what we can see here, this is below, so this region is below percent chance that it's going to be, or this is going to be below normal. This region in here will be equal chance of warmer or colder, and then these regions here, much more likely to be above normal. The darker the color you get, the greater the chance it is to be either above normal or below normal. So in Wisconsin, equal chance of being normal temperatures. Equal chance, could be normal temperatures, could be an equal chance of being above normal, equal chance of being below normal. So that remains to be seen. And then seasonal precipitation outlook, same way, we interpret these the same way. So we can see, so above, it's looking like we could be wetter than normal, the northeast wetter than normal, and then the whole southern portion of the country below wetter than normal, or below, below the probability that they're going to have less precipitation. So here in Wisconsin, above normal, so this will make this all depends. If our temperature is warmer, then it'll be rain. If our temperatures are colder, then we're going to get snow. Or are we going to get this back and forth? If we get warmer periods and more precipitation, then that could set us up even for some freezing rain, which is pretty nasty stuff. So, so we'll see what happens there. And then even looking further ahead to future projections. I'm just showing there was a whole host of different maps that I could have showed as to what's being expected for Wisconsin, and I just kind of focused on two of them that follow along with what I've covered here. So the first is days that are going to be warmer than, what's going to happen with respect to days that are greater than 90 degrees Fahrenheit, through 2041 to 2060. So that's what this is showing. So this is showing the 1981 to 2010 conditions, days with more temperatures that were greater than 90 degrees Fahrenheit. So we can see, there's somewhere around 5-10 days, or 10 days in the southern portion of the state, 5 days in the northern portion. So here in the Driftless area, maybe 10 days a year we get that are 90 degrees Fahrenheit or warmer. However, if we move forward to that 2041 to 2060, it's looking like it's going to be potentially somewhere between 25 and 30 days of the year that are going to be above 90 degrees Fahrenheit. So the hottest, that maximum temperature is going to be warmer than 90 degrees Fahrenheit. Again, these are climate models, so these are simplified representations of the real world essentially. So they are just meant to be models to just kind of give us some perspective on what might happen. And there's some numbering and stuff on here, and that's just simply related to the different model run that they've done, that the scientists have done. And again, this is out of UW-Madison. This is from the Nelson Institute at UWM. And then we can look at precipitation. So these are days per decade with precipitation greater than 2 inches. So here we've got some, maybe we've got 12 days, 10 to 12 days where we've had precipitation greater than 2 inches in the Driftless area, whereas by 2041 to 2060 we could have upwards of 16, even in the furthest south area, 14, 16 days with precipitation greater than 2 inches. Again, remember, these intense events, lots of precipitation following in a short period of time is very problematic. And why 2 inches is used here is because these are terrain, greater than 2 inches in a day is terrain changing precipitation event. Impacts infrastructure as well as impacts the terrain, right? What's happening, washouts, road washouts, all kinds of different things that can happen. Bridge washouts, right, more dam failures, that kind of thing. Okay, so I'm just going to summarize a couple of the points here, and then I've just got a couple of last slides to talk about. So warmer, wetter conditions in the Driftless area over the past few decades with more intense precipitation events. That's pretty, I think everybody can probably agree based on their own experience as well. Future projections indicate we're going to continue to see these trends. So, and then those change in climate normals indicate the warming is most pronounced during fall and winter, with precipitation increases tends to be in spring and fall. So that's just kind of the takeaways from those normals data that I showed you. So I teach climate change a lot to my students, and sometimes it gets like it's all this doom and gloom, right? And so let's talk about some positive things that have happened, right? So if we consider climate change and what causes climate change, and it's the increased, essentially it's the burning of the burning of fossil fuels that puts more carbon dioxide into the atmosphere. So where has there been some good news that's associated with this? So if we think about some of the steps that have been taken, as well as what's happening with emissions here in the United States. So U.S. emissions have been declining since 2007. You know, post the economic collapse, that's where we really started to see a decline in U.S. emissions. This is also due in part to greater fuel efficiency. Fuel efficiency, greater, more efficient, we have more efficient appliances in our homes. There's a whole host of reasons why these U.S. emissions have been dropping. So here we've got, so this is since 1975 is what this graph is showing. 2020, we had a big dip, right, because of COVID during the pandemic. There wasn't as much production occurring, so therefore we had this drop in emissions. In 2021, we had a little bit of a bounce back, but we're still, we're still in pretty good shape. I'm curious to see the newer numbers. This type of data is put out by the EIA, the Energy Information Administration, I believe is what that stands for. And it takes them a long time to compile this data. These charts are always a couple of years behind, so I'll be interested to see when the new numbers come out as to what's happening with 2022 and 2023. Sources of U.S. electricity generation is changing. This is a good thing, right? We're using less coal, we're using more natural gas, we've got way more renewables. Solar both solar and wind power have taken off. Under the Obama administration, he came up with a plan that said an all of the above approach. And so this was back in 2008 that he started, 2009 that he came out with this. You can't just shut down fossil fuels because you have to kind of wean people off of them. But he really invested heavily in renewable energy sources. And wind power really took off, and also has solar power. So those have been really good initiatives that have continued because they're good for business, right? It's not, don't just stop doing them because companies have realized that these are good for business, so they're sticking with it. We saw a little, and we're seeing, so that decline in coal is a really good thing simply because that's the dirtiest of our fossil fuels. So 60% of our energy is from fossil fuels, 19% from nuclear, and 21% is now from renewables. When I started teaching the climate change course, I think maybe 4 or 5% was from renewables, so I'm seeing that to be a good improvement. And then we're seeing more electric and hybrid vehicles. These definitely reduce the amount of emissions, right? Electric vehicles, no emissions. Hybrid vehicles, reduced amount of emissions. So this graph, these are just showing the vehicle models that are available by powertrain in the U.S. So this is 2014 to 2023. So these are non-hybrid internal combustion engines, and then this is just this portion of the graph expanded. So here's our hybrid vehicles, we've got plug-in hybrid, and then we've got our battery electric. And the battery electric is really taking off just because the technology is getting better. And the same with the plug-in hybrids as well. And then, even better, number of registered light-duty vehicles. So this means people are actually buying them, right? So these are not just produced by different companies, but people are actually buying these. And we can see, we're getting, 2 million, a combination of 2 million plug-in hybrid and battery electric vehicles were registered in 2021. So that's a real step in the right direction. And then, of course, the electric vehicle charging stations, the availability of them has increased so much as well, which is, we've got really great distribution of them across the United States and also in Canada. Canada's improving as well. So if people have these electric vehicles, you got to have somewhere for them to be able to plug them in, right? And then thinking about what can we do, this is what I always say to my students, right? And so, back to all these basic things, improve energy efficiency and conserve energy, right? Turning off lights, just all that basic stuff, unplugging appliances, which I don't always do. I always think about it, but maybe not at the right times. Walk, bike, use public transportation. This is something that my students and I, when I bring this up in class, this is a real problem for them. These students, 85% of our students are from Wisconsin, and the majority of them are from somewhere other than La Crosse. So therefore, and if they're in small towns in different parts of the state, they don't have any way to get there. They have to own a car. I can't believe the number of students that own cars. You know, it's incredible. When I was an undergrad, people didn't own cars because they couldn't afford them. But students need to have cars because they need to have some way to get home. So it's, you know, the improvement in transportation is really, really important. And the addition of this Borealis train has been remarkable, right? 18,000 passengers within, what was it, within the first month? They had 18,000 passengers, and they just surpassed 100,000 passengers. There was a celebration in La Crosse a couple of weeks ago, which is...
Since May?
Since,
Sorry.
No, you're fine. So it started in May, yes, and then within a month they had 18,000 riders, and they just celebrated 100,000 riders the other day. They're talking about putting another train in. Yeah, another Borealis train. Yeah, I've taken it. It's great. It's great. We were right on time. It was terrific. You can really count on it. And we've also got on campus, La Crosse has Drift Cycle. So right, these bikes that you can I'm not quite sure how it works. I used to live in Toronto, and I used to use a similar thing there. So it was pretty handy. You just pay by the amount of time you use it. It's pretty economical. So if you don't have a bike, it's an easy way to get around. And they're in different spots all around the city of La Crosse. And I know that there's a whole ton of other cities across the nation that are doing similar, that have a similar system in place. Shop local, buy sustainable. Again, not so easy for my students, but probably easier for people who have jobs or have an available source of income. And then eat more plant-based foods, right? I tell them I only eat, I try to only eat meat a couple of times a week. And sometimes it can be hit or miss, but you know, that's always important. And then just the basic rules of just trying to take better care of the environment. You know, everything is so disposable now, right? Things just don't last the same way. I sound like my father when I talk about this stuff, but it's true, right? These things just they simply don't last the same way that they used to. Unfortunately, I get very frustrated when I buy something and then, I get 2 years later and it's not working, right? When I was a kid, we had the same one for, felt like 15 years or something. So that's pretty much, I guess that's a good spot to wrap up, and I'd be happy to take any questions.